Hello and welcome back to Calculus 1, section 4.4 on graphing functions by hand without a calculator, right? So we're going to use our brain rather than a calculator. Now, fast graphing, at least sketches of the graph, are very important to make quick snap decisions. In some areas that's important, in some areas of work it's not. But even though we have technology to graph literally anything today, um, it's still good to know this because it gives you the insight into analyzing functions. And that's actually more important than being able to graph them. It is all the analysis that will come in, and we're going to put all of the concepts from pre-calculus and calculus learned so far together to come up with this idea of how to graph functions by hand. Obviously, this was crucial to know, just like 70 years ago when there were no calculators, or even 50 years ago, calculators were not. Well, none of them were graphing anyway. Let's go 30 years ago, maybe. What is the TI 83, I think, was pushed out in 1998, 1999, something like that. These things are not too old. I mean, ability to graph without brain has been maybe just in the last, let's say 30 years. Prior to that, for the existence of calculus of over 400 years, right? You had to use your brain if you wanted to graph something. Now, there is also a middle school way of graphing, which is you compute y values, but that one could give you incomplete picture. So to give you an example, let's say your function looks like this. So you have function do something like go through and then follow this asymptote here, and then have another piece like that. That's possible, right? To have something like this, and you pick points -2, -1, 1, 0, 1, and 2, and you make a chart of values for -2, -1, 0, 1, and 2, and you compute their y values, whatever they are. You're going to completely miss this very exciting part of the graph. And if this is the energy graph in time, this is where your project explodes, because it's trying to pick up infinite energy, and infinite energy in a short amount of time over here is called an explosion. So designing things, right, it's important for us to have bounded graphs. It's important for us to have to know if any one of these things occur and so on. And simply, using the method of what we learned in middle school, where you plug in x and you get y, which always works, but you would have to do that for a wide range of values, and it's more time consuming than obviously using the method that we are going to do. But also, right, the fastest thing is to do it on the graphing utility. So, right, using the computer, and we'll verify our graphs today using Desmos, obviously. All right, so let's go and take a look at one of these problems before what I call a shopping list. Shopping list of things we calculate before we shopping list to graph the function. There we go. So what is on the shopping list? Well, number one is domain. We could find range, but it's not necessary. Number one, domain. There is no talk about that. Then we want the x and the y intercepts. And that's a joke because for x-intercept, you set y equal to 0, and for y-intercept, set x equal to 0. So that's a joke. That's your algebra 1. Number 3, asymptotes. And you have 3 of those. Vertical, horizontal, and slant. Oblique, slant. Yeah, that's your chapter 2. And this is your algebra. And this is your pre-calc 1. Number 4, first derivative and second derivative. That's your calc 1 calculation. And number 5, first derivative test. That's also from calc 1. Number 6, second derivative test. Also calc 1. 7, not used a lot, but maybe we can exploit symmetry. Now, symmetry is the concept of even, odd. And that's your pre-calc 1. 8, additional points. Now, additional points, that's going to be your middle school. So pre-algebra, I guess. I can call it algebra as well, whatever. Where you pick x, compute y, right? Pick x, compute y. We will see when this kicks in. It will, right? And number 9, graph and win. When you separate these into their individual calculations, I believe it works out to be 13 different calculations. So we have domain, x, y intercept, 3 asymptotes, 2 derivatives, we're up to 8. First, second derivative test, we're up to 10. Symmetry, 11. Additional points, 12. And the graphing is on the 13th. Yeah. So you're not always going to have all of them, but these problems can easily take like 30-40 minutes. So for the exam, you will have a separate first derivative problem, first derivative test problem, separate second derivative test problem, separate problem for min and max, right, which will be the part of the first derivative test anyway, right, min and max. So all of these separate problems. And then your graphing problem, you will get all of this information computed, and you will show the skill of drawing the graph, knowing these details. So there will be no function for you to cheat and plug into the computer, right, and then just redraw the shape. So the chart with values that we compute now will be given, and you will have to do those, just like that limit problem on a first exam, where I gave you those 5 different facts about the function through the limit, and you were supposed to draw the graph. The same situation is now with this. All right, so now we have our shopping list. We are not learning any new calculus here. We're just going to put all of that algebra, pre-calc, and calc calculations together to graph function by hand. So let's immediately jump into the homework section and pick a problem to graph. We're going to start obviously with some polynomial. something that it's relatively cheap, and then move on with maybe inverse tangent and some more interesting things. Problem 18 should be a joke enough. 3x minus x cubed, and we know that the domain is all real numbers. I need that for partitioning later on. X-intercept is 3x minus x cubed equal to 0. We factor out x, we get 3 minus x squared. And we get x equals 0 and x equals plus minus root 3. So I have 3 x-intercepts, 0, 0, which at the same time is a y-intercept as well. Root 3, 0, and negative root 3, 0. This information is something that I will be graphing. These are what you call a live point, right? So that will be graphed. Now, when you get the 0, 0, that's immediately the y-intercept as well, and you can only have one y-intercept. Otherwise, it's not a function, right? Because of the vertical line test. So I don't have to do this, where I plug in zeros in each x to calculate the y value. But we already know that that's the point. So I just, for the sake of completeness, I put it there. But as soon as you get 0, 0 on the x-intercepts, that's your y-intercept, and you're done. Okay, asymptotes. No asymptotes because f of x is a polynomial. They don't have asymptotes of any kind, ever. When you just have a vanilla polynomial like this. If you divide polynomial by something, sure, as soon as you have a denominator, right? And then ln and e, they all have. Sine and cosine don't have asymptotes, but then the other four do. Inverse ones, again, have or do not have asymptotes. So you have to be careful, right? But in this case, no asymptotes. Now, that's generally bad. When you have a problem without asymptotes, that's generally bad because you have less stuff to graph, less stuff to guide your lines. We don't like the problems that don't have too much going on because it's hard to draw the line, right? The more asymptotes you have, the more points you have, the more of everything you have more information to graph. And yeah, this is actually very unfortunate, but we'll live. First derivative, right? So we're going down the list. We knocked out domain, we knocked out intercepts, we knocked out asymptotes, and now we need to deal with earlier lecture today. First and second derivative, and compute first and second derivative test. So I'm going to go and find the first derivative. Now the function was 3x minus x cubed, so that's going to be 3 minus 3x squared. And I'm immediately going to find the second derivative to use it later, which is negative 6x. That's our life. All right, first derivative test. Now, again, this is something that I will need. This is something I will need. I just want to highlight them so I can find them quickly. So for first derivative test, we are setting our problem equal to 0. And if you divide the whole thing by negative 3, you get x squared minus 1 equal to 0, which spits out plus minus 1 critical points. Ooh, looks like we're going to have our min and max. Or maybe those are concavity changes. We'll see. So partition immediately. Where do I partition? On critical points and vertical asymptotes. I don't have vertical asymptotes. So my negative infinity to positive infinity domain is partitioned at negative 1 and positive 1. Test points, clearly -2, 0, and 2. I compute my first derivative at -2, which is 3 minus 3 -2 squared, and this is less than 0. How do I know? Well, -2 squared is positive times a negative, so that's going to be a much bigger negative than 3, so it's less than 0, and I have a decrease over here. Then I have the first derivative computed at 0. Well, that's just going to be 3, which is larger than 0, so I have increase. Now, I did tell you earlier that for polynomials, these things are going to alternate, but if the polynomials is mixed with something else, they won't. So maybe you shouldn't be remembering it. I don't know, whatever. We are done with our first derivative. And we also found that we have a minimum at -1 and maximum at 1. So we can go ahead and figure that out. So minimum at -1, comma. Now I need to go put -1 in the original problem. And that's going to be -3 plus 1, -2. -2, I hope. So this value was f at -1. And then we also have a max, which is at 1, comma. And when you plug in 1 over here, you get 3 minus 1, which is 2.
So for the future, don't try to use any neat tricks. Just kind of go through the motions. Don't try to be like do any weird stuff with that, like you were saying.
The stunts are great when you know it well and when you're comfortable. So I definitely qualify for stunts, right? I've been doing this for almost 15 years. And this is how we are not equal yet, right? One day you might get far beyond of what I learned in mathematics. But right now, the Padawan Jedi Master, right? We don't get to use the same tricks, right? Does it make sense?
Yeah, no tricks for us. Got it.
Because experience teaches you when the tricks can be used, and if you try to force them every time, right, and try to skip some steps and cut corners, it might backfire in a way that you are not going to like it, right? And I show. So for polynomials, I said for polynomials, they will always alternate, right? But if you mix a polynomial with sine or e or ln, it might not. But then if you just memorize that as soon as you see a polynomial, it alternates, and you disregard the part where, if e is paired with it, it's not going to be the case, and then you just alternate it, it's going to be wrong. So these are the things that we have to be very, very careful about. So yes, I would say no tricks, but again, you will pick your poison. All right, so first derivative test gave us a lot. We have additional 2 points, min and max. We have function going up and function going down. The second derivative test will give us the concavity, because remember, your increase in function can go this way, but your increase in function can also go that way. So it's not enough just to know increase and decrease, because both of these parts are increasing, but this one is concave up and this one is concave down. The same thing goes for a decrease. You can decrease this way, you can decrease this way. This one is concave up, this one is concave down. And they are both decrease. So it's not enough for us just to know increase, decrease. We need to know concavity. Now, if you have concavity without increase, decrease, you're good. So second derivative test now is the second derivative equal to 0. We had that as a -6x. And that one gives us x equals 0, inflection point, and our partition. negative infinity to positive infinity with a 0 in between. We can pick literally any test points. You see how my test points for second derivative test were partitions for the first and a 0? Kind of they swap their roles, right? Because they compute different things. So now I have negative 6 times negative 1 gives me positive 6, which is bigger than 0, concave up. And second derivative, so negative 6 times 1 is equal to negative 6 less than 0, concave down. I have all of the information I need, but just for fun, we'll say f of x equals 3x minus x cubed is odd function because you have only odd exponents. So you, for now, until you are done with Calc 2, with chapter 11 of Calc 2, you have to memorize that sine is odd, tangent is odd, cosine is even, then secant is 1 over cosine, so secant is even as well. So you have 4 odd trig functions and 2 even trig functions. This has to do with symmetry because when the function is odd, has odd, when function is odd, then it has the origin symmetry. And as I said, most famous would be, right, sine x, because this is symmetric through the origin. Where the even, which is a cosine, cosine has this y-axis symmetry. So every even function will have a y-axis symmetry, like x squared is even, it's an even exponent, and it's a symmetric on the y-axis, right? Y-axis goes directly in the middle of this. So the symmetry helps, and again, that's a pre-calculus story, right? Talk even and odd functions and a symmetry all the way back in pre-calc 1. So, you can review that because sometimes it does help with this. I don't need additional points because I already have those 5 points. If I need more, I will compute more. It will come up later, don't worry about it. So let's graph. The way you graph is you put your xy, right, coordinate system, and then you start placing all of the values. I always start with asymptotes. Unfortunately, we don't have any. So let's go and pick up the stuff that we do have. Now all of these values are like 1s and 2s and root 3s. So I can use 2 squares to be one unit because the graph is kind of big and these numbers are small. So here we go. I'll go 1, 2, 3, 4. And then 1, 2, 3, negative 4 on this. And then 1, 2, 3 here. And then negative 1, negative 2, negative 3 here. Let's graph them all. What do I have? Negative 1, negative 2 minimum. Negative 1, negative 2 minimum, meaning smiley face through it. It's a minimum. And then 1, 2 maximum. 1, 2 maximum, frown. Because it's a max. So it's a frown. Frown. Happy. Minimum. Maximum. All right. We're done with that silly thing. And what else do I have? I have a 0, 0. We calculated that one as your inflection point. So you have your max graphed, you have your inflection point graph, you have your mean graph, and now we want those intercepts. Well, 0, 0 was one of the intercepts, and then we had negative root 3 and positive root 3. Now, that's about 1.7 blah, 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 right? So 1.7 blah, 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 right there, negative root 3. and 1.7 blah blah blah. There's you go, your root 3. Have you ever did the connect the dots and then colored? Well, this is the same connect the dots, just no coloring. You have to connect this, 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 and this in one continuous line, because there are no vertical asymptotes to interrupt that continuous line. So we just connect this. Let's go. Connect it down, connect it up, connect it up, connect it down, and then just shoot out of these points, because the domain is infinite, right? They're going to go forever. So it seems like that this graph has a squiggle there and then goes back down. Why is there a squiggle here? Because concave down changes into concave up and then goes up. And here's your graph. Now, we can use concave up and concave down features to make sure that all of this makes sense. Do I have inflection point at 0, 0? I do. Right? I didn't write it here, but inflection point 0, 0, which at the same time was x and a y intercept, so they all lined up. So that's our inflection point. Concave up. Oh, that was bad. There's no squiggle here. It goes straight through. There's no squiggle. It goes straight through. Because, you see, the way I had it was wrong. I had it like this. You see, then there has to be another inflection point, because this would be concave up and this would be concave down. See the way I had it, like this, curving like that? That was bad. It has to go straight through, straight cut, because when it's a straight cut like this, it's concave up. The whole time is concave up. All right, so there we go. That's fixed. So I have concave up to the left of 0, concave down to the right of 0. Perfect. Now I should have a decrease, increase, decrease. Decrease, increase, decrease. Good. Yay, that's it. We got it. Let's take a look at a spicier case. I want a rational function, then I want maybe inverse tangent or something beautiful along those lines. Let's take a look at problem 33. It looks evil enough. F of x is equal to x squared plus 12 divided by 2x plus 1. We all see that we cannot factor the numerator, right? X squared, we cannot factor that one because it's plus 12. Okay, that means that it will definitely not cancel with the denominator, which has this issue point at -1/2 when you set denominator equal to 0. So -1/2 is a vertical asymptote, which immediately ruins our domain. So we have interruption at -1/2. Now I love the vertical asymptote because it gives me more stuff to follow, right, through the calculation. So domain is there. X-intercept is when I set the whole thing here equal to 0, because you set y equal to 0. And when you cross multiply, you get x squared plus 12 equal to 0. And the solution are complex. That means no x-intercepts. That's a big deal. Guys, your line, your graph is not cutting through x-axis anywhere. From -infinity to +infinity, the graph is not allowed to cut through x-axis. That's a huge deal. Now y-intercept is going to be 0 squared plus 12 divided by 0 plus 1 is at 12. So we have a 0, 12 y-intercept. I'm going to mark this as something that I will draw. So cool. I actually have a lot of stuff already. Let's see how about our asymptotes. Now we already said that the vertical asymptote is at x equals negative 1/2. And I didn't do any limits or anything like that because the numerator does not factor, right? If there was a factor up there that could cancel the 2x plus 1, there would be no vertical asymptote. But nothing cancels in this problem, therefore your good old set denominator equal to 0 is good enough. Now for some spicier problems, you have to use the sledgehammer, right, which is the limit from 2.4. But in this case, we don't. Now, horizontal asymptote. We know for rational functions from pre-calc that when the degree on the top is bigger than the degree on the bottom in denominator, there are no horizontal asymptotes. So ha, none. The reason why I picked this is because it has the slant asymptote. And for whatever reason, you can't divide polynomials. So that's why I picked this number. When you have a slant asymptote, you have to divide polynomials. Was that minus? Plus 1. And then you need to put in this placeholder, plus 12, right? You have to put the placeholder, let me just check. Yes, plus 12. So for slant asymptote, they only happen, here I'll write it in blood one more time, only when the degree p is by 1 larger than the degree q. And I'm just going to say x to the p divided x to the q. So now you understand where this stuff comes from. So when the degree in the numerator is by 1 bigger than the denominator. So that's a 2, that's a 1 on the bottom. So 2 is bigger than 1 by 1. So there we go. So now to do this long division, I have to say how many, right? It's x squared divided by 2x, which is x over 2, which is 1/2 x. Now you multiply 1/2 x back, you get this plus 1/2 x, and now you subtract. These guys cancel. Now this is intermediate algebra. And you get negative 1/2 x there plus 12. So now you need to divide negative 1/2 x by 2x. And when you do that, when you do this, you have negative 1/4, x's are canceled. So minus 1/4. And there's your equation. I don't care about the remainder and all of these kind of things. That's just, yeah, whatever. So the best practice when you are dividing these polynomials is to actually not be lazy and write the stuff that I wrote on the side. Now I erased it because I want to write it one more time. When I'm dividing x squared by 2x, I am dividing x squared by 2x, and when I cancel, I get x over 2. And that is the same as writing 1/2 x, which is my first value there. When you do the whole algorithm and you get your negative 1/2 x, that needs to be divided by 2x again. So x cancels x, and you just have 1/2 half divided by 2. Well, half of a half is a quarter, so negative 1/4. And that's how I have this part. So now I have my slant asymptote as y equals 1/2 x minus 1/4. This is the reason why I picked this problem. It has the slant asymptote, and I'm going to use that. All right, time for calculus. We're done with asymptotes. We're done with intercepts. We're done with the domain. Let's go do some calc. F prime of x. We use quotient rule, or you use your logarithmic differentiation. Clearly, logarithmic differentiation, if you can do it in your head, is going to be way faster and better, because why? You're getting your problem factored, right? And you are doing it very quickly without doing any of the ridiculous products and chains and all of that stuff. But I'm going to do the quotient rule just because I can. So that's going to be 2x plus 1 squared. There is another derivative technique that I didn't show. Actually, let me write the function here. The function is x squared plus 12 divided by 2x plus 1. And then we're going to take the derivative here using the chain rule. So we take the denominator, write it as is, square it, then put that denominator here, square the top, derivative of the top, minus, copy the top, times derivative of the bottom. There we go. And then you simplify this. That's going to be 4x squared plus 2x minus 2x squared. Right, this one needs to distribute. That's not a square, that's times 2 from the derivative of the, there we go. So minus 2x and then minus 24 divided by same 2x plus 1 squared. And I need this as simplified as possible because I need to find second derivative as well. So that's 2x squared plus 2x minus 24 over 2x plus 1 squared. Now, you do see that you can factor out 2 on the top, right? I hope you do. So 2 times x squared plus x minus 12. That's a huge help, actually, because now it's a joke to solve it equal to 0. So I have my first derivative here, but I will use this one to do my first derivative test. Well, I can use this one for everything here, because when I start taking now second derivative, right, when you take the second derivative here, this 2 gets copied. It's a constant. And then you just have a quotient rule again for all of this nonsense here. So 2x plus 1 squared times the derivative of the top is 2x plus 1 minus copy the top x squared plus x minus 12 times the derivative of the bottom, which is 2x plus 1 to the first power times the chain rule from the inside, another 2 over there. And that works out to be what? That's my second derivative of x is 2 times, and now, square this 4x squared plus 4x plus 1 times 2x plus 1 minus x squared plus x minus 12 times 8x plus 4. I did the 2 times 2 is 4 and multiplied in. 2x plus 1 raised to the 4th power. Ooh. No. Do not distribute this. 2x plus 1 times 4 in the right there. Look at this. Dead. There we go. So, second.
Professor, wait, Professor.
Yes.
If you didn't in the first in the first, the 2x plus 1 squared, couldn't you just not foiled and you could have canceled that as well?
Are you talking here?
Yeah, in the numerator, 2x plus 1
I don't
squared.
have enough of them because I only have one on the second one. So I have to foil this because I can only cancel one of these. Right? If you look at the top, you can only factor this one and this one. And when you factor those, they cancel with the one on the bottom.
Oh, okay, I see. Okay.
So I don't have enough.
Okay.
Right? If the second one was squared over here, then I could cancel this one, that one, and 2. But I only have 1. So this one is limiting. This term is limiting term. All right, so what do we have? We have 4x squared plus 4x plus 1 minus 4x squared minus 4x minus plus 48. Ooh, shiny. They're all canceled, guys. You see that? 4x, negative 4x squared, 4x, and 4x gone. So it's just a 49 over 49 times 2, right? It's 96. No, 49, it's 98 over 2x plus 1 cubed. Oh, I never showed you the cool way to take derivatives. Hold on. X plus 1 cubed. I need to blue this one because we will be back, and I put the blue on this one. Another way, maybe even faster than logarithmic differentiation, I'm not sure. You see the problem? You circle it like this. Do we all see it circled and selected?
Yep.
And then you push math, and then you select an action, and you say differentiate. Oh, I selected the wrong one. So you circle, you push math. Oh no, I did the good one, actually. Oh, it gave you factors. See, 2 times, and then it gave you factors. Yeah, that's good. So that's the faster way to differentiate. It works really great. All right. First derivative test. Now we're going to need those factors. FDT. We take our first derivative, 2 times, it was x squared, was it plus or minus x? Plus x minus 12, divided by 2x minus 1 squared, or was it plus 1? Plus 1? All right, fine. And you set that equal to 0. And this is where you need your factors. So 2, and then you have your x plus 4, x minus 3, divided by 2x plus 1 squared. And when you cross multiply, denominator dies. So you only have 2 equals 0. There's no solution. But x plus 4 equals 0 gives you a critical point at negative 4. And x equals negative 3. X minus 3 equals 0 gives you x equals to 3. So I have these two critical points which we are going to use for our partition together with the negative 1/2 vertical asymptote and all of that. So now partition, and here is our vertical asymptote finally, right, making the appearance. Negative 4, negative 1/2, and 3. So these are our partitions, and we pick 4 test points: negative 5, negative 1, 0, and 4. And now we have our derivative. Where is it? Okay, so I'm actually going to use this here for the first derivative test because I just don't want to compute this stuff. I don't want to compute this. I just want to go and say f prime of -5 is 2 times -5 plus 4, -5 minus 3, divided by always positive number. This 2 is always positive number. I don't need them. I can delete both of these things. When you square a value on the bottom, being positive or negative, it doesn't matter. The answer will always be a positive number. And if the answer is positive number, when you divide, whether it's a positive or negative on top, it will remain that because you're dividing by a positive, right? Positive divided by positive is positive. Negative divided by positive is negative. So whatever the top is, when the bottom is positive, it's always whatever the top is the answer. So we're doing this analysis. We're just cutting out these needless calculations. I have a negative times negative. So the whole thing is a positive value. Because altogether, I have a positive number times a negative number times a negative number divided by another positive. Altogether is a positive larger than 0. Increase. Plug in a -1. What do you get when you plug in -1? You get. So now we know we can ignore these two because they don't really contribute. So what do I have? I have, with a -1, I have a positive here, and a negative minus is a negative. So, boom, decrease. Put in 0. Positive times negative, another decrease. Plug in 4, all positive, increase. And look at your arrows. Up, down, down, up. This is why you cannot memorize, right? Oh, I'm just going to have polynomials and I'm going to alternate. So you can do the other ones to fill in the blanks when you study, right? Where you need this one, you need this one, and you need this one. I use the analysis to skip through that and save on time. But now, what I found is that this one is a max. What happened? Oh, this one is a max, and this one is a min. I found that by looking at the graph. And obviously, look, the vertical asymptote, it's not going to show min or a max, right? It can't, because you can't have a point at the vertical asymptote. So that's it for the first derivative. Second derivative test. Remember, each problem is like 30-40 minutes, so such is life. We had something simple. We had 98 divided by 2x plus 1 cubed. That was it, right? Yeah. And when you set this equal to 0, there's no solution, which means no inflection point. But that doesn't mean you don't get to do the second derivative test. Remember, if you have vertical asymptote, you always partition with the vertical asymptote. And even if you didn't have the vertical asymptote, then the entire domain is one partition. You can always do first and second derivative test. If you have nothing, you still have the entire domain being one partition, and you have to check one number everywhere. So in our case, we do have the partition at -1/2, right? Because that's the VA. We partition on vertical asymptotes and inflection points. I don't have any inflection points. So vertical asymptote is all I have. So -1 and 0 are my values here. Now cube doesn't work the same as a square, right? The square makes the number always positive. The cube and odd exponents preserve the sign you have inside. So when I do my second derivative test for -1, I have 98 divided by -2 plus 1 cubed. This is a positive divided by a negative, gives me a negative, so less than 0, concave down. Second derivative computed at 0 is 98 over 1 cubed, and that's positive divided by positive. I know the answer is 98, but I don't care. Positive divided by positive is positive, so we are getting concave up. Good. We have our concavity. No symmetry, because this function is not even a rod. You have this vertical asymptote that ruins everything. You have the slant asymptote that ruins symmetry. So no symmetry here because of asymptotes. We're ready to graph. And then I might have to call upon extra points. I don't know. I don't know until I put everything I have on the graph and then see what else I might need. Go ahead with the question if you have a question. All right, so now I'm going to make, let me see, what are the largest values we have? We have a -4, we have 3. Yeah, so we're going to go with, again, 1, 2, 3, 4, -1, -2, -3, -4. And then we're going to have these guys as well.
Professor, do we need to go up to 12 because the y-intercept is 0, 12?
Say no more. Oh, actually, I know. I'm going to draw this by. The tablet is at a weird angle because I don't have space over here. There we go. So let's see if this is my 12. That's the 0 level for x-axis. That's our y-intercept. And now the biggest problem here, well, I can still keep the scale here larger. So -1, -2, -3, -4. 1, 2, 3, 4. The scale is, you know, 1 square this way, 2 squares that way, but it's going to be easier to see. Okay, so we have that. And then what are our max at -4, min at 3? Oh, I did not compute the y values for those. Bah. -4 in original problem. There we go. That's 16 plus 12 divided by -8, -7. This is 20. This 28 divided by -7. That's -3. Okay, so that's -3. -4, -3. That's the one that I need to graph. And then the other point will go here as 3, let's plug in, see what. There we go. So 3. That's 9 plus 12 divided by 7. That's 21 divided by 7 is again 3. Okay, 3. So 3, 3. Yep, there it is, 3, 3. All right, so -4, -3, -4, -3, and 3, 3. Now, -4, -3 was a maximum, so it gets a frown. 3, 3 was a minimum, it gets a smiley. Now you would say, well, hold on, how can maximum be lower than a minimum? It can.
They're local. So.
Very good, they're local, yes. So max at -4, -3, and the y-intercept. Okay, now asymptotes. I have the asymptote. I like to use red. I like to use red for -1/2. That's my vertical asymptote, x equals -1/2. And then I use blue for horizontal and slant. You can't have them at the same time. If you have slant, you don't have horizontal. If you have horizontal, you can't have slant. They can't show up at the same time. So blue is always good to use for that. And you can have nothing, obviously. Now, the formula was, what was like 1/2 minus a quarter? Okay, 1/2 minus a quarter. So 1/2 x minus 1/4. Now, this is going to be, pain in the neck to do it, but -1/4 is right here. And we are supposed to go up 1 unit and 2 units over. So up 1 unit is here, but then 2 units over we have to go by the units of x. So this is our scale. So it's going to look like this. I don't like this. Or do I? So down and over and down. And, oh, okay, it missed it. Okay, good.
So I can't believe I'm asking this, but I don't know if I haven't remembered or I just wasn't told. The slant asymptote has the same function as a horizontal asymptote. At infinity, it approaches the asymptote still, right?
Yes.
Okay.
And the functions actually can cut through it, just like the horizontal. Yeah. So vertical asymptote, that's why I put vertical asymptote red. You can't cut through it. All right? But this one you can. All right, so now let's see. One thing that we immediately see that we can do is connect, right? Have this follow my vertical asymptote, go through 12, and fall down into this. And then, see, this slant asymptote is going to go like this forever. So this is going to give us a minimum there, and it's going to bend and eventually start following. So that's where the minimum is, the 3, 3. So it goes from up there into it, passes through, and then bends to follow. Now we want after to have a concave up piece. We do have a concave up piece. And then we want to have a decrease up to 3. In between the asymptote and 3, we want to have a decrease and an increase after. See how everything fits? Everything is perfect there. Good. Now, the other side is going to be, again, tricky to draw, but such is our life. We have this asymptote going forever this way. So the line will come in, hit the maximum value, and then bend to follow this one and go forever like that. So now to see the whole graph, I just have to do this because, you know, it was drawn larger, but you can see the whole graph. And this is the first one. I'm actually going to go to the Desmos to recreate this graph over there by typing in the function, obviously. So we have our min and a max. So this was your minimum. Here's your max, which was -4, -3, I believe. And so 1, 2, no, the -1, -2, -3. There we go.
When we're drawing this out on a test, do you want us to label it with max, or is just the coordinate point fine enough?
Yeah, I mean, I see that it's a max. I'm just, you know, reinforcing that visually for students who still say, okay, your max is lower than your min. And your comment on, oh, it's a local one, it's perfect. That's exactly what it is. But you see that you can have the maximum points to be below minimum points.
But for full credit on a test, we just need to label it with a coordinate point system. Like,
yeah, coordinates are fine. Yeah, that's yes. Same like in algebra course, right? This one is immediately labeled because it's on the axis and all of the points that are off. So you do not have to write a min because I can see it's a min. It's just, you know, I have to do it now. All right, so now I have to bring this back to its original size. That's good. Yeah, actually.
Hey, Professor.
Yes.
I hate to jump back to part of your analysis, but when computing the when using the second derivative test and the first derivative test,
yeah.
When it comes to an exam, do you want us to approximate the values? Because
I don't care.
Oh, so you can.
I just need this.
Okay.
So I assume that vast majority of people will plug in the number in a calculator and come up with a number on the other side. I just don't want to be bothered doing that. I do the analysis because it's faster, because I don't like using a calculator. But you are not going to lose any points if you have that all of this is equal to 17, which is bigger than 0, right? So whatever. I like the analysis because it gets me through these, you know, long problems faster. That's it. That's it. All right, you're welcome. Let's jump to Desmos, and over here in parentheses, type the top part, which was x squared plus 12. So we have.
I can't see Desmos.
Yes, because I am terrible. That should fix it.
Yep.
So we should have x squared, x squared, and then plus 12 divided by, I don't need the parentheses, but that's okay now. I don't need them now. 2x plus 1. There we go. So they have a -4, -4 minimum, which means that I calculated that wrong. They have a 3, 3 maximum. Okay. So I know now that I have to go and fix that. But I hope you guys, if I do this, I hope you see that there is a vertical asymptote at half. It does go through 12. I got that right. It does go through 3, 3, but I have -4, -3. It should be -4, -4. So you see the asymptote, and then you don't really have the formula for your slant asymptote, but you can definitely see that the graph is following some kind of slant asymptote there. All right, so going back to my problem here, new share, and this one, there we go. And I'm just going to cheat over here, put -4, -4, and go up there and fix that thing here as well. There we go.
Oh, you had it. Yeah, you had it right before. You just put -3, -3 for some reason. It looks like.
Yeah, it's -4, -4, and 3, 3.
Yeah, but like up there it says that you should. Yeah, it says x equals -4, but for some reason, I guess you just looked at the minimum and put it right. You didn't make any errors in your math, is what
No,
I'm
I
noticing.
did. I had this as -3. I computed -3,
Oh,
so
okay. Okay.
Yeah, he's referring
I'm
to the
bad with
y.
numbers.
You're referring to the x.
Yeah.
Yeah, but yeah, it's fixed. So -4, -4, and yeah, that's that. All right, one more, and then we'll take the break. Now, again, guys, you have polynomials, rational functions, radical functions, trigonometric functions, logarithmic functions, exponential functions, mix of all of them, right? So it would take me literally 10 hours to go through just every one of those plus, some mixes of them. 10 hours. You have to study. You have to try things that you haven't seen. And then if you run into a brick wall, right, let's talk. Bring it to office hours, bring it to class, bring it to review, ask questions. I haven't done inverse tangent in this class at all. So I just want to try and flex a little bit, see what we can do with this one. And call it for this section. Take a break and then do 4 or 5 afterwards. So x squared over √3. The break will be a little bit longer, right? This time after this problem. So maybe you can go grab some food, like 10 minutes or so. Grab some food and something. I'll play the epic music. All right, so let's go and take a look. It's a 5-hour class, so right. Yeah, there it is. Boo. What now? Well, domain is clearly -infinity to +infinity. And you're going, what do you mean clearly? Well, for me, is clearly because I know that the graph for inverse tangent is this. So I am allowed to plug in any value in here for x squared. I can put positive, negative numbers, whatever. Dividing it by a number is still a number, and then the tangent will always give an answer to all of that stuff. So, yeah, -infinity to +infinity, and this is just inverse tangent of x. But since the composition, right, function composition here allows for any numbers, right? This would be different, guys, if this was inverse tangent of ln x divided by √3. Well, then you're in trouble because now you can't use negative numbers and 0 because of ln, right? ln spoils the fun for the full party, right? But in my case, it's x squared. And x squared, yep, you can plug anything, just like you can plug anything in here. Now, also, if this was inverse tangent of, I mean, we're talking pre-calc 1 now, but still it's important. 1 over x. Well, negative infinity to 0 union 0 to infinity, because the only value that would make your problem explode is 0. Because when you divide 1 by 0, you get infinity, tangent of infinity is infinity, and that blows up. I mean, sorry. Tangent, it will give you pi over 2, but you can't plug in 0. There are horizontal asymptotes here. I forgot to tell you that. So inverse tangent of infinity is pi over 2. So we have this now. We have the domain. I'm going to get rid of all of this stuff. You can go back in the video and play it a few times to do the what-if analysis. I have my domain and I need my x-intercept now. And that's tangent inverse of this mess equal to 0. So you hit both sides with a tangent. And you get your x squared over root 3 equal to tangent 0 is 0. Multiply everything by root 3, you get your x squared equal to 0, and you get your 0. So you have 0, 0, which is x-intercept and y-intercept at the same time. I told you that before. So that's going to be one of our points to behold. Now, asymptotes. Nothing weird happening in there, so no VA. Now, horizontal asymptotes are something that inverse tangent does have at pi over 2 and negative pi over 2. Now, that's something that you learn about the function, right? This is not communicated to me in a dream, right? I opened the book and I learned. So horizontal asymptote at y equals pi over 2 and y equals negative pi over 2. It's just something that you have to know for inverse tangent graph. Just like you know your horizontal asymptote for e to the x is y equals 0. 1 over x is y equals 0, right? So for inverse tangent are these two. And now we are ready for our first derivative. Now, inverse tangent derivative, I'm going to write it here on the side. The derivative of inverse tangent of a function is derivative of the function divided by 1 plus function squared. So the function that it's inside the inverse tangent is x squared over root 3. So I have 1 plus x squared over root 3 squared plus the derivative of it, which is 2x over root 3 on top. The derivative of, right, you have 1 over root 3. That's a constant. You copy that, and the derivative of x squared is 2x. So now you fix this as much as you can because you don't want this double fraction floating about. You have your 1 plus x to the 4th divided by 3. And you multiply top and bottom here by 3 root 3 to kill off all of the denominators. So f prime of x is equal to root 3 and root 3 will cancel, so you get just 6x on top. On the bottom, you get 3 root 3 plus, now 3's are canceled, which is root 3 x to the 4th. Now, we still don't like this root 3 in denominator, so I'm just going to get rid of that one as well. Multiply by root 3 over root 3, called rationalizing. And get 6 root 3x on top. And on the bottom, I have 3 times root 3. That's a 3 times this one is 9. Plus, and then root 3 times the 3x to the 4th. And now I can see that I can reduce everywhere by 3, which means that this was a mistake over here. But hey, and we get 2 root 3x divided by 3 plus x to the, so x to the fourth plus 3. So here's my first derivative simplified. 2 root 3x divided by x to the fourth plus 3. And I'm going to put that in my blue so I can find it quickly. I need second derivative, and then we can do the first and second derivative tests. Quotient rule. How about logarithmic differentiation? That would get us there quicker. We have 2 root 3x divided by x to the fourth plus 3. Right, that's raised to the first power. Times the derivative of all of this. So I have 2 root 3 so you would have this as ln 2 root 3 x, right? That would be the top. And if you break this apart, it's ln 2 root 3 plus ln x. Now, this is a number, and derivative of that kills it. So it's just 1 over x for the first one. Minus, and now you have the derivative of this, which is keep it as is, and put its derivative on top, which is 4x cubed. If you don't like logarithmic differentiation, go ahead with the chain rule. I am not going to force you one way or another. I just like this because now it's easier for me to work out the equal to 0 part. So I have my second derivative done the boss way. First derivative test. Take 2 root 3x over x to the 4 plus 3 equal to 0 for our critical points. That gives me 2 root 3x equals 0, from where x equals 0. So x equals 0 is something. I don't know what. Actually, I'm going to move all of this stuff to the side so I can do my partition here. So I'm moving this here. There we go. And I can calculate immediately y of 0. Go back to the original problem. That's inverse tangent of 0 over root 3, which is a big fat 0. So we have a 0, 0, which we are going to write to be a min or a max or something, right? So we have our 0, 0 there. Partition. No vertical asymptotes from negative infinity to positive infinity. And we have just one of these at 0. Now, before I pick my points, I want to take a look what kinds of functions I have. Do I have trig? Do I have e? Do I have ln? Right? Because we talked about it earlier. I just have this basic, right, plug in and pray. So -1 and 1, whatever. So f prime at -1 is going to be a negative number divided by always positive number, because x to the fourth is even, and that's always going to spit out positive number, and then plus 3 it's more positive. So this is less than 0, so I have a decreasing function here. And then I have f prime at 1, which will give me positive over positive. It's more than 0. So I just found out that this is a minimum. Awesome. second derivative test. And this is where my second derivative, done logarithmic differentiation really shines, right? Because I have it in a factored form. What was that? 4x cubed over, no, x to the 4 plus 3 equals 0. The reason why I love it is because it's factored, and I can just say this equal to 0. And that spits out the same 0 as before. And then we have this one. And that one is solved easily because all you need to do is to move this one to the other side and then cross multiply. So it's a joke. So this is 4x cubed over x to the 4 plus 3 is equal to -1 over x. Cross multiply. This is basic algebra. So you have your 4x to the 4 equal negative x to the 4x cubed. No, 4x to the 4 when you multiply by x. Yeah. So when you multiply by x, 4x to the 4, and then minus x to the 4 minus 3. So when this x goes to the other side, it becomes 5x to the 4 equals -3. And that has no solution immediately because you have even exponent equaling a negative number. So there is no IP. But we still have negative infinity to positive infinity domain. We have no vertical asymptotes. And, oh, we got a 0. So, test points, again, you can do -1, +1. And this is now where you are at disadvantage with this because you have to now plug into this mess. So, it's never a free lunch. So the test itself is harder. Equation is easier. You might want to multiply through to have the form which you can use to compute the value. Because look, when you distribute this one into both, right? When you distribute, because that's your second derivative, that's where you want to do your test. You want to plug in 1 and -1 into this one here. If you distribute this, you'll have less calculations because you have 2√3, x and x cancel, over x to the 4 plus 3, and then plus, now this becomes 8√3 x to the 4th divided by x to the 4th plus 3. So now when you plug in your value of 1, you see that everything is positive, so that's concave up immediately. Because 1, the bottom is always positive no matter what. This is always positive. So this is always a positive number here. And when you plug in a -1, -1 to the 4th power is always positive. So this is concave up as well. Now you would say, well, hold on. What happened with x equals 0? Guys, we already determined that x equals 0 is a minimum. So if I have a big fat concave up piece, there's your minimum at 0. Right? So calculations will sometimes give you things that you have to think about. You can't just aimlessly go and say and claim things, right? That's the way life works, right? Cool. All I need to do is to graph this and I'm done. I just want to make sure one more time. Okay. So let's see what the graph would look like in this case. I don't know. So I have this tablet spazzed and just dump this, whatever. There we go. All right, so what do I have? I have a 0, 0 right here, which turns out to be, we said a minimum? Minimum. So it's going to have the smiley face through it. And we have the horizontals, and then a decrease and an increase. Okay. So if I place my pi over 2 asymptote in here, that's roughly 1.5, right? And I need this to be concave up. So yeah, I don't like this. Because the concave up, I have it as a decrease on this side, increase on this side. See, if I draw like this, then there are inflection points actually here because these pieces are concave down. There is something weird happening here at this problem. So inverse tangent should always give us values between negative pi over 2 and pi over 2. This graph needs to look like this, but then that's just gonna hit. You know, that's just gonna hit like this. And I don't see it later bending down because I don't have a maximum. I don't have extras of any kind. So something is wrong somewhere. Well, instead of wasting time, let's cheat. Let's see.
Professor, I just graphed it, and it looks very similar to what you didn't want it to look like.
Yeah, but I don't like that it doesn't have extra critical. You know what? Let me go one more time. What I don't want it to look like, I don't want it to look like this.
Yeah, and that's how it came out.
But that means that I have another 2. Did I do calculation over here wrong?
Yeah, it looks like there are 2 inflection points. I just don't know where. Or I can see where, but I don't know how to get where.
This is plus 3, right? So the 4 plus 3, that's a minus there. I copied this sign wrong. Look at the blue up there. Right? So I copied this sign wrong, and because of that I got no solution here. If this is a minus, then this is a plus, and when that's a plus, then this becomes a 3 you know what? Because we have to get this, I mean, you can't have an exception and say for this problem it doesn't work. It has to work for everything. So that's a minus there. All right, so now I have 4x cubed over x to the 4th plus 3 equals to 1 over x. Cross multiply, you get 4x to the 4th equals x to the 4 plus 3. That's 3x to the 4 equals 3. X to the 4 equals 1. Holy nightmare. X equals plus minus 1. That's why the whole thing looked weird and bad. Because of the wrong sign. And I didn't catch it because even the one that I did the check with had the wrong sign. And obviously it didn't work. So my partition is not at 0. My partitions are at, I mean, you can put 0 as well, but that's a minimum. -1 and +1. There they are. Okay, good. You see, you can see that you did something wrong all the way when you get down to the graph, and then you have to start from scratch. So yeah, such is life. All right, so now my test points are -2, 0, and 2, and we plug those back into the problem. Now we can use the simplified one over here. And in this case, we actually have to compute because you have a subtraction in between. So pick your poison whether you want to be computing here or you want to be computing in the orange one. I don't care. But we actually have to compute now. So I am going to delete this graph that was no bueno. And we're going to compute the second derivative test. So f double prime at -2 is going to be 2 root 3 over x to the 4th. So that's going to be -2 to the 4th plus 3 minus, and the second one is 8 root 3 x to the 4th, which is -2 to the 4th divided by the same -2. Well, at this point I should combine them into a single one, so I'm not writing this 15 times. There we go. And there's a minus here, and then just one denominator. All right. So 2 root 3 minus 8 root 3 times 16 divided by always positive number. So this is negative, so it's concave down. This is 8 times 16, right? That's a lot, and then 2 minus a lot is going to be a negative number. So that's a negative divided by a positive, less than 0. Okay, now 0 is going to make 2 root 3 survive, but put it -0 divided by 3. That's a positive. And then when this one is positive, it doesn't change anything on a first because, yeah, it doesn't change anything, so concave down again. So f double prime of 2 is the same thing because when you put the even power, which is 4th power, when you put that to a -2 or to a +2, in either way you are going to get the same value at the end. Now I have correct information to draw the graph. Finally. So if I call that 1 and I call that 2, then my vertical asymptote of 1.57, right, which is half of pi, 3.14. That's my pi over 2 horizontal asymptote. Should have been blue, but such is life. 0, 0, and then I have my 1, 1, and my 1, 1 critical points. Oh, sorry, inflection points. So we have a smiley, and then it bends out following the asymptote. It doesn't bend down again. It can't bend down because there will be a maximum. So that this side is bad. There we go. Follows the asymptote. There we go. So that's our 0, 0. That's our 1, 1. And negative 1, 1 points. Well, are they 1, 1? I didn't compute. That's a lie. What are those points? Inflection points, IPs. That's inverse tangent of 1 squared over root 3. That's inverse tangent of root 3 over 3, and that is pi over 6. And pi over 6 is not 1. Pi over 6 is about 0.5. So those are bad values there. It's a pi over 6 on the... There we go. It's a pi over 6 on the y-axis. All right, let's cheat. We are going to do this inverse tangent. So arctan. You don't like the capital letter, I guess. There we go. Arctan of, we need x squared. So x squared divided by is there a square root symbol here? No. 3 to the 0.5. Wait, what happened here? Oh, I never escaped the x squared. There we go. X squared divided by, there we go, 3 raised to 0.5. There it is. Whew! So you can see it's about 1.5, the horizontal asymptote, and you can see that it's concave up in the middle and concave down on the sides. You also
Professor,
can see the decrease into 0 and increase after 0, which matches our calculations. Yes?
we're not well, I can't see the
I keep forgetting to share this. The YouTube is seeing it. I keep forgetting to share for the Zoom because, as I said, I've been doing this method of teaching for 5 years, and I've never used Zoom before. So now Zoom is an additional annoyance over here, and I keep forgetting to switch to Zoom to share when I go to a different page.
On Zoom, can't you set it to share your monitor, your entire
Yes.
monitor instead of just the one program?
Yeah, but the problem is that sometimes, especially when I'm streaming and doing all of these things, you know, things just pop up on the screen, like the names and things. So I'm trying to kind of keep it really with a bare minimum, right? Because it goes also to the YouTube, and I don't want your names and stuff to pop up and all that stuff. So it's just annoying. But I was thinking actually to scrap streaming on YouTube altogether because there's just so many of these lectures already there. Each one is like hour and a half, 2 hours, or hour. So this lecture is at least 15 times for an hour and a half on YouTube. Every time, different examples. So if you just come to Zoom and learn without YouTube, and I'm really thinking about it because YouTube now, well, YouTube, the streaming off of this tablet is really warming it up. I'm actually using ice packs to keep it cool because it just can't process Zoom plus the websites plus the encoding, video encoding and streaming, right, and all of that stuff. It's just this is a bare minimum, right? It's a school issue tablet, so obviously they cheaped out and bought the cheapest possible one because the one that I actually need is $2,000 more than this. so yeah, it's kind of it's really hard. But anyway, you guys have the lecture. You've seen 3 examples. You just repeat the whole process over and over and over again on every problem you get. The question is, can you get derivatives correctly done, right? Can you do calculations like me? Right? Not mess up with copying the negative there and all of that stuff. But we haven't learned anything new in terms of calculus here. We just took everything we ever learned so far and put them all together in this one lecture where the problems can go all the way up to 30-40 minutes per problem. So hopefully you guys will do well on that. Let's take a break.